Limits to infinity. So now, instead of focusing on coming into a point from the left and the right, what we want to do is we want to evaluate the end behavior of our graph. Okay, what's going on at the ends of our graph? The ends of our graph is when x is traveling out here towards positive infinity and when x is traveling out here towards negative infinity. Well, here we have ourselves a parabola, and these arrows tell us what's happening. If you see arrows at the end of your graph, you are guaranteed it will never change direction again, and it will continuously go in the same direction forever, in that direction. So, if you can see from this graph, as x is going towards infinity, the y values keep shooting up towards positive infinity. But you actually have the same thing here. As your x values keep traveling down towards negative infinity, well, all of your y values are also shooting up towards positive infinity as well. So that's what we mean by limit to the infinities, checking out the end behavior of our graph. Over here, this we looked at in an earlier video, but I just want to now focus on something different. I want to focus on the limits to infinity. On this graph, graphically it's easy to see as your x value. So when x is 2, y is here. When x is 4, when x is 6. All right, so all of these are your y values, and every time your x value gets closer and closer to infinity, as x is approaching infinity of this function, notice how all of your y values are approaching the number 2. Let's check the other side. If you look over here, negative infinity, what is the limit of our function as x is traveling down towards negative infinity? Well, here are all of our points, right? When x is negative 8, when x is negative 10, negative 12. All right? Every time x keeps getting closer and closer to negative infinity, all of your y values are approaching the same value too. You may remember from last year that when the limit of your function as it's traveling towards the infinities equals a numeric value, that's your horizontal asymptote. We have a horizontal asymptote at y equals 2 or f of x equals 2. And I think you can see that. I already drew it in. Let us consider this when evaluating limits going to infinity. We said earlier that these two things are polynomials unto themselves, right? So let's consider each separate polynomial, the numerator versus the denominator. So I'm telling you that limit is going to infinity. Well, when the x value is going to infinity. We're talking about, x is 1,000, x is a really big number. X just keeps getting bigger and bigger and bigger. So we want to plug in larger and larger x values and see what happens. Consider this. Let's go when x is 100. When you plug 100 in here, you're going to get 100 times 100 times 100 times 16. That's very big. This is nothing compared to what we just said. Negative 2 times 100, that's big, but not nearly as big as 16 times 100 times 100 times 100. Now, this is the largest. Okay, this blows this out of the water simply because of the exponent. Every time you multiply by another 100. All right. So if you see, now what happens when we plug in when x is, a trillion? Well, a trillion times a trillion times a trillion is monstrous. But when you plug it in here, a trillion times a trillion times a trillion times, I don't even know how many times I said it, but 4 times that's the largest in the numerator. What I'm trying to point out is the highest exponent runs the show. Same thing downstairs. This is a different polynomial. But we're doing the same thing. We're evaluating it as x keeps getting bigger and bigger. So again, let's think of the same thing. When you plug in 100, well, this right here, this would be 2 times 100 times 100 times 100 times 100. Wow. This one, if you plug it in, is just 100. And this is just 1. This number gets so big so quick, these two become irrelevant. In fact, the larger x becomes, every single time it gets bigger, the less relevant these two become. Because now, you plug in a trillion, so f of a trillion, right? There's a lot of zeros there. Now, the first term is this. You have 1 trillion, how many, zeros that is, times itself, times itself, times itself. The other terms become irrelevant. Evaluating that is the same exact thing as evaluating this. What you do is you take the highest exponent in the numerator and the highest exponent in the denominator. And they run the show, and they tell you what's happening in the numerator and denominator. So evaluating this is the exact same as evaluating this. Let's simplify. You can simplify this fraction because x to the fourth over x to the fourth is 1 over 1. This reduces to a constant number. This equals 5/2. So when it simplifies to a number, that's your answer. So what is this telling us? I don't know what this graph looks like, but as x is approaching infinity, all of our y values are approaching some number 5/2. Okay? But we're not always going to be so lucky where it reduces to a constant number. When it does, great, we're done. But what about in this case here? Let's look at this one now. Okay. Oh, what is that here? Let me just get rid of that. Okay. Well, now in this yellow one, we have something different. Notice how here's the highest exponent term and here's the highest exponent term. So when I rewrite this, because no matter what, this is the highest exponent, these two are irrelevant. This runs the show in the numerator, and this runs the show in the denominator for the same reason. Let's simplify this one. Well, here when you cancel out your x cubed, and well, here x cubed, we're still left with a 5x. So this is the same thing as x going to infinity of 5x over 2. Now, why do we reduce it? Well, look at it. Would you rather evaluate this thing or would you rather evaluate this thing? That's why. Now let's plug in our x value. Well, x is approaching infinity. All right, so think about this. Like, what happens when I plug in f of 1,000? Well, f of 1,000 is going to give us 5,000 over 2. That's pretty big. What happens when you plug in, a billion trillion? Well, then what you have is you have a 5 billion trillion over 2. And then you plug in a gazillion. You have 5 gazillion over 2. Point being is every time x keeps getting closer to infinity, the value of your y's are also doing the same thing. They're approaching infinity. So the answer to this limit right here, this one is approaching infinity. You can just write infinity, or when the limit is approaching infinity, it does not exist. What about another scenario? I'm using the same type of function here. Here, the green, oh wait. I'm using a very similar function. All I'm doing is manipulating the exponents on that 2x in the denominator there. I want to show you what happens. Now, first, when the exponents are the same, they cancel out and you have a constant. When you are left with one exponent in the numerator, well, now the numerator is getting big and the denominator is doing nothing. The denominator is just staying at 2. It's going bigger and bigger and bigger. It's approaching infinity. Here, though, let's simplify. All right, this is going to run the show in the numerator, run the show in the denominator. That leaves me with, 5x to the fourth over 2x to the fifth. And now when we reduce, I'm left with an x in the denominator. Notice the difference. That is infinity. And I have a 5 and a 2x. Let's evaluate this fraction. Well, we're approaching infinity. Let's start off with 1,000. All right, so when x is 1,000, my y value is 5 over 2,000. And when you plug in 1,000,000, then what you have is 5 over 2 million. And then when you plug in a trillion, you have 5 over 2 trillion, 5 over 2 gazillion. Every time x gets bigger, when x is approaching infinity, this y value, 5 over 2x, is approaching 0. I know you have a 5 in the numerator, but 5 over the largest number you can think of, and it just keeps getting bigger and bigger downstairs, it's approaching 0. Okay? So graphically, it would look something like this. I don't know what the graph does, but as x is approaching infinity, all of your y values are approaching some sort of horizontal asymptote, y equals 0. So what happens when you're traveling towards the other side of the graph, the negative side, right? So, well, when x is approaching negative infinity, well, now you're thinking of numbers like when x is negative 100, what is your y value? When x is negative a million, what's your y value, et cetera, right? And it just keeps getting bigger and bigger and bigger. And you're traveling towards the negative infinity for x. Well, the same thing applies. These are the same functions that we had, that we just talked about. I just am going to save time and start with the highest exponent term in the numerator and denominator. Let's see what happens when you're going to negative infinity. Well, the same rules apply. If you are starting with something like this and you simply can cancel out your variable, well, the same thing, then you're left with 5 halves. Well, if you have a constant, that right there is what your y value is. All right. So what that means is as x is traveling down towards that negative infinity side, I may not know what your graph is doing, but I do know that it is eventually going to approach y equals 5 halves as it gets closer and closer to negative infinity. Now for the green one. X is going towards negative infinity, and the difference here, I think you can see it, is here we cancel and we get 1. Here we cancel, and we're still going to have an x left over because you had 4, right? You had x times x times x times x. Well, what that's going to give you is you have a 5x in the numerator and a 2 in the denominator. Remember, we need the lim until we evaluate. That's when we figure out what the answer is. Okay, well, remember what this is. Now, think about this. So let's just visualize. We plug in negative 100, right? X is negative 100, what do you get? When x is negative a million, what do you get, right? And you keep getting bigger and bigger. Well, let's see what this is. This is going to be, well, this is going to end up being negative 500 over 2. I don't know, that's big. I mean, you're dividing it by 2, but it's still pretty big. It just has a negative in front. What happens when you plug in negative a million? Well, then what you get, right, you're taking a negative a million, and you're plugging it in right here where the x is. So that's going to give you negative 5 million over 2. Oh, you're still dividing by 2, but now it's negative 5 million. Well, think about every time you get bigger. When x is a trillion, you're going to have negative 5 trillion over 2. And then you have negative 5 bazillion gazillion divided by 2. Even though you keep dividing by 2, your number is growing bigger and bigger and bigger with a negative in front. So what's happening is, as your x value is approaching negative infinity, your y values, all of these f of x values, are also approaching negative infinity. There's always going to be a negative in there because of the x value. If it's going to negative infinity, the limit does not exist. Now for the third scenario. In this case, we are going to cancel out the x's here, and because we have 5 of them downstairs, we're going to have an x left downstairs. And that's going to look something like this. You have 5 over 2x. Well, the big difference here is, well, this simplified to a constant, no big deal. Here, you had the numerator that kept getting bigger and bigger and bigger. I don't care what your denominator is. If the numerator keeps getting bigger and bigger, that value is getting bigger and bigger with a negative in front. Yes, it's negative, but it's really big with a negative in front. That's approaching negative infinity. Here, the x is in the denominator. Let's see what happens in this case. So let's visualize. We have, as x is traveling down towards negative infinity, let's stop when x is negative 100. And let's stop when x is negative a million. All right, let's stop there. Let's see what happens. So now you have 5 over negative 200, right? Just plug that into there, multiply it by 2. Now let's figure out what the y value is when x is negative a million. Now you're going to have 5 over negative 2 million. What happens when x is negative blah, 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 bazillion gazillion? You're going to have 5 over negative 2 bazillion gazillion. I'm making these numbers up, but I think you understand. Hopefully you understand think about what's happening. No matter what, the numerator is 5. And this denominator just keeps getting bigger and bigger and bigger and bigger. So what's the value of this fraction every time this thing gets bigger. This is approaching 0. I don't care if the numerator is 5. This keeps getting bigger and bigger and bigger. The value of the fraction is getting closer and closer to 0. So this one is approaching 0. And so this graph, as x keeps getting closer and closer to negative infinity, even though we may not know what it's doing over here, we know that it's getting closer and closer to y equals 0 as it's getting that way. And what that indicates is we are going to have a horizontal asymptote at y equals 0. I realize I never showed you what happens over here, so let's just see. So what this means is as x is traveling down towards negative infinity, this graph, we don't know what it's doing, but we do know that x is going towards negative infinity. All your y values are also going down towards negative infinity. So now what do we do when we have a square root? Well, same thing applies. We're going to look for the highest exponent term in the numerator and denominator. That's going to leave us with this. We have the limit as x is approaching infinity of radical 3x squared, because that's bigger than this one. Think about what this one would be. It kind of has an x to the 0 to it, right? That's 1. So definitely this is the higher term. And then over here you have negative 2x. That's the only term. That has to be the highest term. Now what I would like to do is I'm going to separate that numerator because I would like to focus. I'd like to take out the radical 3 and focus solely on this one right here. That's mathematically equivalent. I am allowed to do that. If you multiply them, you get the same thing back. But what does this equal? Well, yes, you're probably thinking that equals x, and I'm going to say you're right. Okay, so let's continue. And if you do that, now you have this. You have a square root of 3 times an x over a negative 2 times an x. And technically, we still have the limit as x is going to infinity. But now we can cancel that and cancel that. That becomes 1 over 1. And like we said, when it reduces to a constant, that is your answer. Which looks a little different if you're approaching negative infinity. All right, so now what about when you go into the other side of the graph, the left side of the graph? Well, to save time, I'm going to start off with the square root of 3 and the square root of x squared, just like I did over here. And we have a negative 2x. But what happens now when you go into negative infinity? Well, you probably want to still say that this is going to cancel and equal x. And no, it doesn't. No, it doesn't. Technically, the square root of x squared equals the absolute value of x, because it could equal plus or minus x. Right? Think about it. You have the square root of x squared. Well, if this x in here is 3, or if it's a negative 3, well, plus or minus 3 is the same thing. Plus or minus x is what you're looking for. But when is your x positive and when is your x negative? Your x is positive when your x is going greater than or equal to 0. And it seems so obvious, but that's that. If our x values are on the negative side, right, we're traveling towards negative infinity, there's no positive 10, it's negative 10. There's no positive 1,000,000, it's negative 1,000,000. There's no, it's all negative numbers. You have negative x's on this side of the graph. So that's why you substitute it in with a negative x. Please be mindful of that. Let's continue. I have the limit as x is approaching negative infinity of a radical 3 times a negative x times negative 2x. So in this case, I can cancel out an x with an x, become 1. I also have a negative and a negative, which will simplify to be a positive 1 over 1, or however you want to look at it. What are we left with? Instead of negative radical 3 over 2, we have positive radical 3 over 2. That's what we have different.